All right, welcome to Physics Video 9.1. We're going to be learning today about colors. The objectives are listed here. I want to call particular attention to objective number 1 and 2, numbers 1 and 2. In number 1, it says be able to state the primary and secondary colors of light. In number 2, it says be able to state the primary and secondary colors of pigment. All right, today we are going to be largely focusing on light. So here's the deal. In 3rd grade, you took an art class. The art teacher came into your elementary school or whatever and said, hey, we're going to do art. And that art teacher told you the primary colors. And he or she told you that the primary colors were red, blue, and yellow, which is true-ish if you're talking about paints or pigments or dyes or chemicals or ink. All right, that is not what we're going to focus on today. Today we're going to be focusing on light. And the primary colors of light are not the same as the primary colors of pigment. Okay, so just be aware of that. The primary colors we're talking about here are going to be largely about light. So with that in mind, here we go. The primary colors of light are, in fact, red, blue, and green. Not yellow. Red, blue, and green are the primary colors of light. Okay? Now, in the same way that you can mix colors of paint to get secondary colors, you can mix colors of light to get secondary colors. So what would happen here is, hypothetically, imagine a situation where you had I'm totally getting ahead of myself. Imagine I've got a red flashlight. So here's my red flashlight, and out of it is coming red light. Okay? And then over here, I have another flashlight, which is, let's say, blue. And out of my blue flashlight is coming blue light. All right? And I shine that onto a white screen. So what's going to happen here is the screen here is going to be red. The screen down here is going to be blue, but there's this chunk in the middle where they overlap. And that is sort of a purpley color, which is technically called magenta. Okay? But the reason this happens is the frequencies of red light and the frequencies of blue light are interfering with each other to create sort of a whole new frequency, and that frequency is called magenta. So here are the possibilities. The primary colors of light can be combined in pairs to create secondary colors. Those are the secondary colors. It turns out that if you mix red and blue light, you get magenta, which is this sort of purpley color that you've got over here. If you mix blue and green light, you get cyan, which is, as the name would imply, a blue-green color. And finally, this is the weird one. It turns out if you mix red and green light, you get yellow. Red and green light combined gives you yellow. I will show you this in class, all right, where we will do this, what I drew over here, and we'll mix red and green light, and where they overlap, you get yellow. And it's the weirdest thing, but it's true because we're not talking about paints. If we were talking about paints, red and green would give you sort of a poopy brown. Red and green light gives you yellow, the yellowiest yellow you can imagine. All right? Finally, it turns out that if you mix all three of them, if you mix red and blue and green all together, you get white. Okay? Remember, we talked the other day about the fact that a rainbow is caused by white light shining through water drops, and the water drops split the white light up into all the different colors. So if we put them back together, if we take red and blue and green, which are the primary colors in the rainbow, put them back together, you get white. Okay? And it also turns out, although I did not write this down in my notes here, is that no color is black. I wrote that in red. There you go. All right. So what this means is that if you look at an object under a white light, they look the color they are. So here we've got, you can't see it because it didn't translate well, but there's a little light bulb over here. So here we have a white light bulb. All right. Now, before we were talking about white light as being composed of RGB, right? Red, orange, yellow, green, blue, indigo, and violet. Now, all we got to worry about is the primary colors. So the idea is this red, or this white light is composed of red, green, and blue. Okay? Now, remember, we talked the other day about the fact that when you look at something, you see what's getting reflected. So this, if you don't know this dude over here, this is Finn, all right? He's from Adventure Time. All the dudes in this are from Adventure Time. So if you don't watch that, I apologize. But Get on the game and watch it. It's good stuff. So anyway, Finn is looking at the guitar and he's seeing red. So what that must mean is that the red light is being reflected. So Finn goes, hey, there's a red guitar. Right? And by process of elimination, that must mean that there are pigments, chemicals in the guitar, which have a natural frequency that matches green, so the green gets absorbed, and other chemicals that match the frequency of blue, so the blue gets absorbed. All right? Similarly, if we take that same white light and look at a yellow drum, here's my white light. The white light is composed of red and blue. No, that's not blue. Green and blue, right? Jake, the dog, is over here looking at the drum, and he's thinking to himself, dude, because he says dude, that drum is yellow. Well, why is the drum yellow? That is supposed to say drum right there. The drum is yellow because it's reflecting the colors that make up yellow. So if we flip back to our notes here, we learned that yellow, down at the bottom of the screen here, yellow is made up of green and red. So that means that the drum must be reflecting green and red. And by the process of elimination, the blue must be getting absorbed. All right? So that's the deal. Now, the question is, what happens if we have a light source that isn't white? What if we take that red guitar to a bowling alley and they've got some sort of crazy lighting in there? I don't know why bowling alley strikes me, but whatever. What color will it look? Okay, so here's the deal. Let's take that red guitar and look at it in a room where the only light source is blue. Okay, it's a 3-step process. All right, step 1 is ask yourself what the red guitar would do to the 3 primary colors under white light. Okay, so you're going to say, if the object is in white light, what will the guitar do to red, green, and blue? So if this was white light, Princess Bubblegum here would be looking at this, and she would be seeing red, because the red would be getting reflected. She wouldn't be seeing green or blue, which means that the green and the blue must be getting absorbed by the guitar, right? This is your first step. Anytime you're trying to analyze what color an object looks under some color light, your first step is to ask yourself, what will the object do to red, green, and blue in white light? Okay? So that's step 1. Step 2 is to look at your light source. So first of all, ask yourself, what colors make up my light source? So in this case, my light source is made up of blue, and that's it, right? Because blue is blue. It's one of the primary colors. But if this had been like magenta, then you'd have to list blue and red, because blue and red make up magenta. Okay, so that's your second step. And then you say, all right, well, my blue light, because it's blue, is only emitting blue light. So that's your second step. And then your third step is to ask yourself, what happens? Sort of, how will the guitar react? So look, we've got blue light coming in. Over here, we already told ourselves that if blue light hits the guitar, it's going to get absorbed. So zzz, the blue light gets absorbed. Since that's the only light source that we had, that means nothing gets reflected. So Princess Bubblegum is going to look at this and she's going to see a black guitar. Right? It's a black guitar because nothing is getting reflected. It's no colors. Remember? Black is no colors. So she's seeing a black guitar because no colors are getting reflected off of it. Okay? Let's try another one. I am going to cheat by doing, nah, I guess I won't. Yes, I will. All right, so now Gunter's the penguin over here, is looking at the red guitar, but now our light source is red. Okay, so sorry. So our first step is to once again ask yourself what the red guitar will do in white light. So we already know that the white or the red guitar under white light is going to, there we go, do that, right? That's the same thing I had on the last screen. If it's in white light, it's going to reflect red, absorb green, and absorb blue. Okay? So, step 2 is ask yourself what the light is going to do. In this case, it's red light, which means that it emits red light. Step 3 is ask yourself what the guitar will do to the light that's hitting it. So the red light hits it. Our rule says that red light gets reflected to Gunther, and Gunther sees a red guitar. That one's not rocket science, right? Because if you get a red guitar and red light, it's going to look red. Okay? But what if we look at it in a yellow light? Okay? So what you're going to do is you're going to start the same place we did before, which is by saying, what will the red guitar do in white light? And the answer is, in white light, it will reflect red, absorb green, and absorb blue, right? Second step is to ask yourself, what makes up yellow light? Well, the yellow light is made up of red and green. So the idea is, here comes green light out of my yellow light. Here comes red light. Oh, try that again. Zoop. Here comes red light out of my guitar. And then ask yourself what happens. So let's see, the green light. According to my rules over here, the green light's going to get absorbed. The green light gets absorbed. The red light is going to get reflected. And so Lumpy Space Princess, which is who this is going to look at this thing and go, oh my glob, that guitar is totally red. Because that is what is getting reflected. Please remember through all of this, you see what gets reflected. Okay? So that's the deal. Magenta light is basically going to be the same thing. The magenta light is made up of red and blue. We know that our guitar is going to absorb the blue and reflect the red. So BMO is going to once again see a red guitar. Okay? So the deal is, you guys, this guitar is a primary color. There's only 2 colors the guitar can look. It can either look red if the red gets reflected, or black if there isn't any red to reflect. Okay? All right, I'm not, well, I guess we should do cyan. All right, so once again, last one for the guitar, and then we're going to go back to the drum, and then I will, yeah. All right, so there's our guitar. We know it's going to do those things. Cyan light is made up of green and blue. So that's our step 2. And step 3 is ask what happens. So let's see, the green gets absorbed. The blue gets absorbed. And that's it. There isn't any red to reflect. So Lemon Drop over here is going to see this thing, and he's going to see the guitar as a black guitar because nothing is getting reflected. All right? Okay, let's do an example with the yellow drum. Okay, so same idea. Why don't you guys pause it at this point? Do step 1. Step 1 is ask yourself, under white light, what will the yellow drum do? So if white, red, blue, and green. So let's see, if this was white light, what would happen? We would see yellow, which means that the red would have to be getting reflected, and the green would have to be getting reflected, because red and green make yellow, which means by process of elimination, the blue must be getting absorbed. Okay? So then, step 2 is ask yourself what will happen to our light source. So in our light source here, we've got just blue. Our rule over here tells us that the blue gets absorbed. So the Ice King over here is going to look at the drum, and he's going to say, that drum is a black drum, because nothing is getting reflected off of the drum. All right. Under red light, let's see, once again, our our drum is going to reflect red, it's going to reflect green, and it's going to absorb blue, right? That's why it would look yellow under white light. That's always got to be your first step. What would happen under white light? Then analyze your light source. We got red light. Did I say red light? We have red light. The rule tells us the red gets reflected. The treetops over here. So treetops looks at the drum and says, that is a red drum. Ice King. And I will bake it into an apple pie. All right. Yellow drum under yellow light would look yellow. I'm not going to do that one because we are droning on here. Let's do cyan. What if you've got a cyan light? So, our yellow drum under white light would red, green, blue. The red would get reflected, green would get reflected, and the blue would get absorbed, right? That's why it would look yellow under white light. In this case, we've got cyan light, which is made up of blue and green. So our rules are blue is going to get absorbed, and the green is going to get reflected. So Peppermint Butler, I believe that dude is going to see a green drum. All right. So there you go. That's the deal. All right. Now, it turns out, we're moving on to a new thing here. The secondary colors of light, it turns out, are the primary colors of pigment. So at the beginning of the video, I talked about your third grade art teacher, and I said that your third grade art teacher taught you that the primary colors of paint are red, blue, and yellow. And as much as I hate to contradict other teachers, they were lying to you. All right? Very often, I think art teachers use red, blue, and yellow because they are aesthetically pleasing. But technically speaking, the primary colors of paints, pigments, and dyes are magenta, cyan, and yellow. And if you do not believe me, I will ask the internet to prove it to you. You have at home a color printer, or somebody that you know has a color printer, and that color printer has ink cartridges in it. So to prove this to you, I have just Googled the word color print cartridge. I guess that's words. I'm going to now click on the first response. Kabam! Let's see, so we've got some cartridges here. The first one is black up here. That is black. They always use a black one because you use the most black ink, right? Now, the other two, or three, are cyan, magenta, and yellow. You probably on your little iPhone can't tell that that is cyan, and that's magenta, and that's yellow. To you, they probably look blue, red, and yellow. But if you scroll down, you will see that there are a couple of them. So here's the black one. Here is the cyan one. I don't know if you can see that word there, but it says cyan. That is one of the cartridges. If you keep scrolling down, the next one is yellow. Whoops, yellow. And then the last one is, oh, magenta. So if you go home and take a picture of, a cow taking a bath, I don't know why you would do that, and then print it up on your color printer, you can get all the colors of the colorful cow taking a bath. I guess I should have said a rainbow, using just those three colors. All right? So there you go. Bam. Those are the primary colors of paints and pigments. And it turns out that if you mix them, you get the primary colors of light. The primary colors of light are the same as the secondary colors of pigment. It turns out if you mix magenta and yellow paint, you get red. Cyan and magenta paint gives you blue. And yellow and cyan paint gives you green. All right? You must understand that the function of a pigment is to absorb light. If you go to Home Depot or Lowe's, which I actually prefer, and decide, hey, I want to paint my bedroom blue, what they will do is they will pull out a gallon of white paint and then they will add pigment to it. And that pigment, what it does is the white paint, originally the white paint will reflect red, blue, and green, right? That's why it's white. When they add the pigment in it, what it does is the pigment then absorbs the blue and the green and only reflects the red. Okay? And that's what the job of the pigment is. So the idea is if I take colors of light and add them, mix them, it's called additive. Whereas if I mix colors of pigment, it's called subtractive, because pigment absorbs colors of light. I will now show you an example, and then I am all done. We're going to go a little over 20 minutes. I apologize, but then we're all done. All right, so for example, suppose that I took a glob of cyan paint, that is not cyan, magenta paint, and I mixed it with a glob of cyan paint. All right, under white light, my magenta paint looks magenta because it will reflect red it'll reflect blue, and it will absorb green. But the idea is that magenta pigment has a chemical in it that absorbs green. That is the defining fact, or defining property of magenta pigment, is that it absorbs green. That's what makes it magenta. Okay? Similarly, over here, our cyan pigment looks cyan because red, blue, green. It reflects blue and green. So by elimination, that means it absorbs red. But the fact that it absorbs red is what makes it cyan. So when you mix it, here in the middle, when you mix the cyan and the magenta, what happens is this paint contains the chemical that absorbs green, right, because it's got some magenta in it. It's also got some cyan in it, so it has the chemical that absorbs red. The only thing not being absorbed is the color that gets reflected, which is what you see, and that is blue. So that is why you see blue. All right, so when you mix pigments, you need to look at what colors get absorbed by the different pigments, and then whatever doesn't get absorbed is what you see. Alrighty? Alrighty, I'm sorry that was long. We will talk about this and spend some time on it in class. Have a good day. That is